Having discussed about linear accelerators, we will now have our tryst with cyclic accelerators in the lecture number 3. We'll discuss about cyclotron and synchrotron. The cyclotron. Although linear accelerators can, in principle, reach arbitrarily high particle energies, the length and hence the cost of the machine grow with the energy. It is therefore desirable to drive the particle around a circular path and so use the same accelerating structure many times. And this is the principle of a cyclic accelerator. The first circular accelerator to be developed according to this principle was the cyclotron, proposed by E.O. Lawrence at the University of California in 1930. In this photograph, E.O. Lawrence is seen to work in his 60-inch diameter cyclotron at the University of California at Berkeley in the 1930s. A year after 1930, Livingston succeeded in demonstrating the operation of such a machine experimentally. In 1932, they together built the first cyclotron suitable for experiments with a peak energy of 1.2 MeV. To make the particles follow a circular path, the cyclotron uses an electromagnet which produces a homogeneous field of strength B between its two round poles. There are two hollow electrodes in the shape of letter D, inside of which the particles can move in a circular spiral trajectory with increasing radius as indicated in this figure. Radio frequency signal is applied between the two Ds designated as D1 and D2, creating an electric field in the gap between them. The cyclotron apparatus is redrawn in this figure, in which you can clearly see the two Ds and the perpendicular magnetic field. Particles with mass and charge move inside a vacuum chamber in a uniform magnetic field that is applied perpendicular to the plane of their paths. In such a field, a particle with speed v moves in a circular path with radius given by r equal to mv over modulus q times b. To get this equation, we have equated the magnetic force on a moving charged particle modulus qvb and the centripetal force mv square over r. When we rearrange this equation, we'll get the radius as mv over qb. The corresponding angular frequency is given by omega equal to v over r. When we substitute for r, we will get the angular frequency as equal to modulus q b over m. This figure shows the top view of the D arrangement. What you see in blue color are the axial magnetic fields. The radial path of a moving charge is indicated by the dark broken line as shown here. There is an alternating potential difference that is applied between the two Ds that create an electric field in the gap between them. As the positive particle reaches the gap, it is accelerated by the electric field force as shown in the figure. As their circular trajectory passes through the gap between the two Ds, they are accelerated and continue along a new path with a larger radius until they arrive back at the gap half an orbit later. That is, at this point. By the time the particle reaches the gap again, the d voltage has reversed and the particle is again accelerated. The polarity of the potential difference and the electric field is changed precisely twice each revolution so that the particle get a push each time they cross the gap. As the particle enters d1 from the gap, its circular trajectory takes a new radius different from the previous one. The pushes in the gap increases their speed and kinetic energy, boosting them into paths of larger radius. The maximum speed Vmax and kinetic energy Kmax are determined by the radius r of the largest possible path. The speed is given by V equal to modulus Q Br over m and Vmax is equal to modulus Q Br over m, where capital R is the maximum possible radius inside the cyclotron. Assuming non-relativistic speeds, we have the kinetic energy maximum equal to half m v square max, which is equal to q square b square r square over 2m. The maximum energy that can be attained with a cyclotron is limited by relativistic effects. For relativistic particles, the angular frequency is equal to modulus qb over m times square root of 1 minus v square over c square. In the non-relativistic case, we have seen that the angular velocity is equal to v by r. So this is equal to modulus q times b over m. Notice that omega does not depend on the particle velocity at all. This is because as the energy increases, the orbit radius and hence the circumference along which the particles travel increase in proportion. A higher velocity is exactly compensated for by a larger radius, provided that the mass m remains constant. And this condition is of course only satisfied for non-relativistic particles. Classical cyclotrons can accelerate protons, deuterons and alpha particles up to about 22 MeV per electron charge. At these energies, the motion is still sufficiently non-relativistic as the velocity is approximately 0.15 c for the revolution frequency to remain approximately constant during acceleration and hence to fulfill the cyclotron condition. To have a better understanding on the working of a cyclotron, let's try to solve this problem. A cyclotron with RF frequency 2 MHz is used to accelerate protons. If the radius of the D is 50 cm, calculate A. The magnetic field in Tesla, B. Maximum velocity attained by the protons, and C. Energy of the protons. From the fundamental equations, we have omega equal to 2 pi nu, which is equal to q b over m. And from this equation, we have b equal to 2 pi m nu over q. Hence b is equal to 2 times 3.14 times 1.67 times 10 raised to minus 27 times 2 times 10 raised to 6 over 1.6 times 10 raised to minus 19. So this is equal to 0.131 Tesla. To calculate part B, we have omega equal to V over R, which is again equal to 2 pi nu. And from this relationship, we can write V max equal to 2 pi mu times R, where R is the maximum radius of the D. And therefore, V max is equal to 2 times 3.14 times 2 times 10 power 6 times 50 times 10 raised to minus 2. So this is equal to 6.28 times 10 raised to 6 meter per second. In part C, we have to find out the maximum energy of the photons. So this is half mv max square. This is equal to half times 1.67 times 10 raised to minus 27 times 6.28 times 10 raised to 6 the whole square, and this is equal to 3.29 times 10 raised to minus 14 joules, which is equal to 3.29 times 10 raised to minus 14 over 1.6 times 10 raised to minus 19 in electron volts. This is equal to 0.2056 MeV. The synchrotron. If we want to accelerate particles to very high energies, we must take relativity into account. For relativistic energies, the equation of motion for a particle of mass m and charge q in a magnetic field B is dp over dt equal to modulus q times v cross b over c. Equating the centripetal force with Lorentz force, we have m gamma dv over dt equal to m gamma v cross omega, which is again equal to modulus q times v cross b over c. In this equation, gamma is the Lorentz factor given by 1 over square root of 1 minus v square over c square. Note that both the magnetic field and the axis of circular bending are perpendicular to the direction of motion. Therefore, from the previous equations, we can have omega as equal to modulus q b over m gamma c. Or the frequency nu is given by omega over 2 pi, which is equal to 1 by 2 pi q by m times 1 by gamma times b by c. When we expand the Lorentz factor, this is equal to 1 by 2 pi q by m times 1 minus v square by c square to the power of half times b over c. As we tend to see, for this relation to hold during acceleration, either the alternating frequency has to decrease, or the magnetic field has to increase, or both must happen. Machines where the magnetic field is held constant but the frequency is varied are called synchro cyclotrons, and Machines where the magnetic field is changed irrespective of whether the frequency is changed are known as synchrotrons. In electron synchrotrons, the frequency is held constant and the magnetic field is varied. In proton synchrotrons, both frequency and magnetic field are varied. Expression for the radius r. For v approximately equal to c, we can also express the frequency of motion as nu equal to omega over 2 pi. And when we substitute for omega in terms of the radius of the path, this becomes 1 by 2 pi times v over r. Since v approximately equal to c, we have nu equal to c over 2 pi r. But from the previous equation, we have nu as equal to 1 over 2 pi q by m times 1 minus v square over c square to the power of half times b over c. When we equate this with the previous equation, we have nu equal to c over 2 pi r. And therefore, the radius of the path is equal to p times c over modulus q times b. And this is approximately equal to p over 0.3 times b. Here p is in giga electron volt per coulomb, b is in Tesla, and r in meters, and q is the charge of a single electron. From this expression, we see that independent of the nature of the accelerating fields, any given momentum will be limited by the product of the radius of the final orbit and the largest magnetic field that can be supplied. Both the figures of the synchrotron shown in this figure are the same but have taken from two different references. The first figure is from Introduction to Nuclear Physics by A. Das and T. Febel, and the second one is a detailed version of the first one, which is taken from the Physics of Particle Accelerators and Introduction by Klaus Willi and Jason McFall. So both these figures shows the basic layout of a modern synchrotron. The particle trajectory is controlled by bending magnets with homogeneous fields, while the beam focusing is performed by specially designed magnets. The acceleration takes place in one or more short RF structures. The particles are supplied by a pre-accelerator, that is LINAC or a microtron. Electron acceleration using a synchrotron. Synchrotrons in the GeV or higher range of energies have magnets positioned in a ring-like fashion. Particles with energies of hundreds of MeV are injected, often from a LINAC, into a narrow vacuum chamber that passes through all magnet apertures. At the start, the fields are set to low values that correspond to the momenta of the injected particles. The beam particles are constrained by the magnetic field to move in essentially circular orbits within the confines of the vacuum tube. To accelerate the particles to higher energy, RF power stations are placed in some convenient locations within the ring of magnets. Every time the particle passes through the RF cavities, they gain typically MeVs of energy from the electric fields. For this to work, the phases of the accelerating fields for different cavities must keep in step with each other as well as with the motion of the bunched beam. The magnetic field must also increase steadily to assure that as the momenta of the particles increase, the radius of their orbit remains essentially fixed in accordance with the expression R equal to P over 0.3 times B. And most of the space along the ring is taken up by bending magnets. However, space is also needed for general servicing of the vacuum system, the powering and cooling of the magnets, for the RF stations, for the injection and extraction systems, and for other kinds of beam elements. A synchrotron, therefore, has many straight sections along the ring where there is no bending. The accelerated particles consequently travel along circular arcs within the magnets and in straight lines between them. In order to reach design energies, the beam particles must traverse the RF cavities and therefore the entire ring millions of times. Proton acceleration using synchrotrons. With the help of cyclotron, protons can be accelerated up to 10 MeV of energy. But in order to accelerate the particles beyond this value, the proton synchrotron was invented. Proton synchrotron can be used to accelerate deuterons, alpha particles in addition to protons. Using proton synchrotron, protons can be accelerated up to 10 giga-electron-volts of energy. The construction. The donut vacuum chamber of the proton synchrotron is made up of steel. There are 4 quadrants that produce magnetic field perpendicular to the vacuum chamber. The magnetic field increases with time, but the radius of positive charged particle is maintained constant. Working. Using a linear accelerator such as Van de Graaff generator, the protons are accelerated toward the donut chamber. Hence, initially the positive particle such as proton can be accelerated up to 10 MeV. These particles are injected when the magnetic field is small. These electrons then come under the influence of radio frequency oscillator. Moreover, the magnetic field is also increased to keep the electrons in circular orbit of constant radius. In order to avoid any losses due to scattering, the pressure inside the donut tube is kept almost 10 to 6 mm of Hg. As proton completes its revolution, it almost gains an impulse of 1 kV per turn, which increases its energy as well as frequency. Hence, to maintain the phase stability, the frequency of radio frequency oscillator is also increased in order to synchronize it with the frequency of proton. The range up to which protons can be accelerated is higher than the range of electrons. Hence, for proton synchrotron, the radio frequency adjustments are made quickly. The protons of very high energy, approximately billion electron volts, can be obtained using a proton synchrotron. This could be attributed to the fact that the radiation losses for protons are smaller than the losses for electron. When the protons are accelerated to maximum energy levels, then the radio frequency is distorted so that the radius of orbit changes. After the proton gets out of its track, it will strike the target.